All right, we stopped here on slide 5, so I'm going to just go ahead and pick up from that there. As I said, I'm taking the easy way out by using the publisher slides simply because they're actually pretty good. You know, it's a good book. So, okay, I'm not going to go into much detail on these because we've already talked about function prototypes. This feature was borrowed from C++. If you get an old C compiler, you may not need function prototypes, but you run into some serious problems, errors, and warnings, and your code can do some really bad things that they don't match. So the more modern compilers, and I'm not so sure about yours, require the function prototypes. The older versions didn't, and they would use the first declaration as a function prototype. But function prototypes are really a good idea, even if your compiler doesn't need that there. So early versions didn't perform this check. It was possible to call functions without the compiler detecting any error. In other words, you call it, and you can end up with some, fatal errors are good in some respects because the program crashes. The non-fatal errors can cause some bad output right there. In other words, if you're processing paychecks, you may be giving out paychecks of 2 million ringgits to someone instead of 2,000 ringgits. So, I mean, you could end up with some, it's good for the guy who gets the 2 million ringgits until you catch it and they've spent half of it, and the bank wants to take it back. And that has happened, in some cases. There's been cases, at least in the U.S., where someone was overpaid or issued a check that they shouldn't have been. Legally, in the U.S., they can go and collect that money back. It's up there. So I've already talked about that. They talk about the include, and again, if I circle this, it doesn't circle the right place. Right there, and it's not the pen, it's not the computer, it's PowerPoint. It's got a problem up there. But the include pulls them from the libraries. And again, we talked about this up there. This goes into more detail. We've already talked in great detail about this is a function prototype. And it looks just like the first line of the function right there. So this returns an int. These are common programming errors right there. This is kind of an interesting thing right here. In the prototype, you don't need to give the variable names. You can just say int, and that tells it it's got 3 integers coming. Since I copy and paste it from the declaration later on, I include the variable names. I prefer to include the variable names up there, but include parameter names and function prototypes for documentation purposes. The compiler ignores those. So if you look at this right here, this X, Y, and Z, they're ignored by the compiler. So you can name them whatever you want in the header and then change the name when you write the function. It gets rather confusing debugging when you do that. You probably should keep those names consistent between the header and the declaration. I'd rather you don't include names in the prototype than use different names right there. Either do the int, then to call it A, B, C here, and then call it X, Y, Z when you declare it. In other words, don't change the name right there. And of course, you need to have the only difference between the first line of the function or and the prototype is the semicolon. You forget the semicolon in the prototype, it's a file error. So here's an example where maximum is going to return an integer, and our prototype has the word void. When I write the function down below and I put int, it's going to give an error. They don't match. right there. This gets into some other issues right here. Right here. Here, of course, we're telling it that cohesion of arguments. In other words, if you change the type, and it's allowed as long as it's numeric or char, because char is treated as a character is treated as a number within the system. A string is not, but a character is. That's there. So if 4 happens to be, in this particular, 4 is a integer because it doesn't have a decimal point, and I tell it that I want to printf, %.3f, that I'm telling it that I want to print it as a floating point number with 3 decimal points. So it's going to print it as 2, even though I passed the square, the square root of 4 is 2, but it's going to print it as 2.000 as a floating point. So, right there. And this kind of goes into that there. Conversions can lead to incorrect results if you aren't careful. Right there. So square root double, if you convert a double, in other words, if you have a floating point number that's declared as a float or a double, and your function's expecting an integer, it's just going to truncate the value. So that can cause you that there. If you have a large integer that's a rather large number, and you change it to short, within the function, it's going to possibly change your value. So you try to be consistent. It's okay if you declare something as float and you pass it an integer because it just converts it to a floating point number. That's okay, but when you're dealing with floating point numbers and you're relying on the compiler to convert it to integers, you can end up with problems. Same thing with shorts and longs as far as integers goes. So usual arithmetic apply there. I'm not going to there. Now if you've got mixed type expressions, I guess is what this is saying. In other words, you got floating point, you got integers in the same expression. It's going to convert everything to floating point before it does the calculation. So if you have, for example, x is equal to 3.0 times 4, right there. 3.0 is a floating point. 4 is an integer. We have to assume that x is a floating point right there. So you'll probably get an error warning if this is declared as an int, because the result of this multiplication is going to be a floating point because of this 3.0 right there. So it's converted to the highest type, whatever takes the most number of bytes. So if you've got an integer in there, it's converted to a floating point. If you've got a double in there, it's converted to a double. If you've got a long double, it's converted to a long, everything's converted to a long double. So everything has to be converted to one type before it can do the calculations. Right there. And the result is going to be whatever's the highest type. Now if you're saying x is an integer and you're going to have it do a floating point operation, it's going to give you a warning, an error, or it's just simply going to truncate the, and it depends on the compiler. Different compilers handle things differently right there. This goes on that side. So again, this just goes through the same thing. And there's really nothing in this discussion that's going to affect their. These are the various types of right there. I think we've seen lists like this before. Printf, you've got long floating, long double, double float. Those are our 3 floating points. Those have decimal points right there. So note that you have an uppercase L for the long floating point. And normally you would almost never use long double. Long double is if you're doing calculations that need to be really, really precise, such as the angle trajectory to reach Mars. If you're off by 0.00001 degree, then you might miss the planet altogether. But if you're calculating the balance of my checking account, you could probably get by with float. Might even get by with short. Right there. Integers, you got unsigned long int, which I've never used. Long int, which I've never used. Unsigned long int, which I've never used. Long int I've used. Unsigned int I've used. Int I've used. Unsigned short, and char. Those are the various types that you can have. And notice that they're all, the scanf and the printf declarations are almost the same, with the exception, I thought there was one exception. Yeah, the double. Printf, you just use the print %f, and the scanf is LF. That one's the exception. Everything else are identical. I knew that there was one. A value can be converted only at their. So in other words, if you know that you should not, you could do what they call a cast operation. I don't worry too much. I don't do that. But again, we can do the word int, then a lower type, and converts there. I'm not gonna, this class I'm not gonna get into using casting that there. If there's no function performs its own, right there. Again, we talked about that. Always include function prototypes right there. If function prototype is placed outside any function, it's got to be by itself. As a general rule, you place all the prototypes at the beginning of your code before main. So your code, typically, when you look at the order of your code, it's going to be, first thing you're going to have is all your comments right there. It tells what your code is. Then you'd have all your includes right there. Then your function prototypes. Then main right there. And then your functions would be after main right there. That's the normal way that you would write your code right there. And each function would have a little comment section at the beginning saying what this function does. It can either be one line above it, or it could be within, after the function declaration right there. And there are several examples of that right there. I'm going to skip this whole discussion on the stack. That's more of a subject for microprocessors. But the stack is how data is passed back and forth between functions in the calling routine. The data is pushed onto the stack, which is a temporary holding place in memory right there. And then they're popped back out when they go into the function, and the result of the function is pushed onto the stack and popped back off at the calling routine. When we're working with C, we could ignore the stack. In other words, it's all handled for us behind the curtain. We don't need to worry about it. If you're writing code for a microprocessor in assembly language, then you have to deal with the stack a great deal. So, but for this class, I'm going to skip any discussion about stack and stack frames right there. And again, I'm skipping all that there. And for your homework, you don't need to worry about dealing with the stack. And since there's no final exams in this class or exams, we don't need to worry about stack. Okay, standard library. Each library contains a header file. We covered that already. We talked about the fact that we use standard I/O. stdio.h. We include that in every program. If we're going to use sine and cosines and other math functions, we use math.h. If we want to use the system clock, we would use time.h. There's all kinds of, there's probably 50 different libraries in there. We're only going to use a couple of them in this class. We've already talked about two, math and standard I/O, and then later in this discussion we're going to use time.h right there. So we use the pound sign, or the, I don't know, what do you guys call that little hashtag? Yeah, hashtags are, that term was actually invented when Twitter came out. They started calling them hashtags out there. So since I've been around before Twitter, a long time before Twitter, I didn't grow up with the hashtag name. We called it the pound sign. And I don't know why we call it the pound sign, because in the U.S., if we have pounds, we put the abbreviation LB after it. So I've never seen the number sign used that there. But again, so include square.h if we had a prototype and a header file. You can write your own, design your own header files. I've done that. That's there. When I've worked on some large projects, we had files that contained nothing but functions. That's there, because our code was relatively large, and we put all of our functions that did a particular thing into a single file. That there, and then we created a header file for those particular files, and we would include those. That there. We won't get into creating header files, but all a header file is, you just, instead of putting all the header files like I showed earlier before main, all those function prototypes, you just cut those out of there and just create a .h file and just stick those into it. That's all that you do there to create your own header file. Right there. Here's some examples of some that there. Assert, we're doing it. That there. C-type for testing characters. Air numbers. Float. That there. Limits. These are math. That there. You can overwrite functions in the library. An example of that would be if you're doing, say, an embedded processor and you have a LCD display, you would have to write your own printf function. That there, or write char or whatever, anything that you would normally write to the display, because you don't have a display, you have to write those functions yourself. You would give them the same name, and you would have to include those in that there. This class we won't do that there, but about the only ones we're going to use in this class are math, time, and standard I/O right there. And you can see standard libraries. Actually, standard library is another one you could use. Those are used if we want to convert strings to numbers and that type of stuff. That there. And then we also have string.h if we're going to do a lot with strings. That includes things like to upper, to lower, in order to change all your characters from lowercase to uppercase to lowercase. Those functions are all contained in string.h. And then time is if we want to play with the system clock and time right there. So I kind of alluded to this before. We're not going to go that there. There's two ways of passing arguments to a function. One is passed by value. That's the way we normally do it. The other is passed by reference. When we do a printf, we're passing by value. In other words, we include the name of the variable. If we want to be able to change that function or that variable, we have to pass its address. And that's referred to as pass by reference right there. So when an argument is passed by value, a copy is made, and we can't change it in the function. Is that my phone making noise? No, that's something else making noise somewhere around here. I hear something, I think it's out in the hallway. Up there. But we can change the value of that variable within the function, and it doesn't change it in the calling routine or the rest of the code. It only changes it with that there. If we call it by reference, we can change it. And the way that we do that is we put the ampersand or the and symbol in front of it, and that tells the compiler that we're going to pass the address or the reference to that variable. And we do that with scanf. So when we do scanf, we're passing the address of all the variables. Otherwise, we can't change it. And I talked about that before when I referred to your bank account. That there. The value is your current balance if you look at a bank account, but the address to it or the reference is the account number right there. So again, there. So normally we pass almost 90% of the time by value. Pass by reference should only be used with trusted functions that need to change that there. You can see all arguments are passed by value, but once we get into arrays, those are always passed by reference right there. But again, we're passing by reference with scanf. And the reason you would pass by reference for any other function is if you want to change the value of 3 things at the same time or 2 things. And that kind of goes against this concept that a function should only do one thing. And if we want to change the value of 3 different things, then we would have to pass the address of all 3 things. The exception is scanf, obviously, right there. But if I had a function that say, well, even if I read an analog digital converter, I would return the value that I read there. So for this class, I'm not going to get into how we how we write functions where we deal with the fact that we've got a reference other than when we get into arrays. And arrays will probably be about where I end this class, chapter 6, right there. So, okay. Here we're going to be doing random numbers right there. And if you look at the assignment I just posted yesterday, you have to throw some dice and play a game called craps right there. It's explained in the book. I won't go through it unless on Monday you want me to go through it and explain how the game's played right there. But it's a game that's played at casinos right there. Obviously, my goal is not to teach you how to play the game. And if you did the simulation for a lot of games of craps, which I've had people do, you'll find that over the long haul, you always lose. Right there. And, one of the things I learned my first course in probability is that you never go into a casino and expect to win. You never win in the casino long term. You might walk away with a few rings the first time you go in, or once in a while, but if you go long enough, you always lose money. And casinos are beautiful places, aren't they? With nice chandeliers and all these beautiful lights and everything else. Those aren't paid for by people making donations on their way in or out of the casino like they do at the masjid. Those are paid for by people losing their money. So just keep that in mind that even though I'm having to use a game of chance just simply, but that's the easiest way to show how to do random number generations. So typically when we do a random number generation, I'm just going to jump across all this there. But we normally use this rand modulus 6. And that produces a range of integers between 0 and 5 right there. So that's how we would throw a dice. If I want to pick a card out of a deck of cards, it would be rand 52. There's 52 cards in a deck. If I want a random number between 1 and 6, say, or 1 and 5, saying there's 5 doors, and you're going to pick one at random, you know, at there. So this is a typical function right there. And the function prototype for RAND is in the standard library. So now RAND picks a number that's between 0 and a very large number, right there, the max int, right there. And it can be, you know, depending on which compiler, it can be 32,767, or it can be 2,148,000,000, something like that there. But usually you just use a RAND function. So this is scaling. We shift that. So when we throw a dice, it's between 1 and 6 right there. And the actual random values are chosen may vary by compiler. Random numbers are not purely random right there. I mean, they use an algorithm for calculating the random numbers. They're close enough right there. So that's there. Now, one of the things I should point out that when we look at we're going to throw 2 dice right there. 2 dice gives you a value from 2 to 12. You can't do a random number and add 2 to it. You have to throw each dice separately. And the reason is when you're throwing dice, to get a 2, there's only one combination, a 1 and a 1, right? To get a 3, you get the combination of 2 and 1, or 1 and 2 right there. So there's 2 ways of getting a 3 right there. To get a 4, you've got 1 and 3, or 3 and 1, or 2 and 2 right there. As you can see, we've got the probability of getting a certain number between 2 and 12 with 2 dice is not uniform. And the way we handle that is that we do die 1 plus die 2. This is a random number between 1 and 6. This is a random number between 1 and 6. And we add the 2 together to get our throw of our dice right there. So if you look at the craps game, and the code is here, it's probably where I'm going to finish class today, right there. But that's how we throw the dice. So here's how we would get one number between, right here, pick a random number between 1 and 6, and I'll put it right here. And this simply keeps track of how many we're printing and just does. So this is going to print 20 numbers right there. So right there, and we get a 66556. These are all fairly random numbers, you know. And if you ran this, you would probably get something different right there. So now if we want to throw a 6-sided dice 6 million times, here's a code that will do that. So we've got the frequency between 1 to 6. These are unsigned integers. We keep track of how many times we throw that there. So roll is between 1 and 6 million. That's in a for loop. And we simply say that the face is equal to 1 plus random modulus 6. And that percent sign, you would say that's modulus. It's the integer remainder is what that is. So I don't know if that's an announcement that called. And we just simply have a case statement where we look at that and we just increase each one of those until we finish all 6 combinations. So every time we throw a dice, and the dice throw is right here. This is where we throw the dice right there. 1 plus random modulus 6. And then we look at each one of these And if it's a 1, we increment frequency 1, 2, we increment each one of those right there. And here we just print out the results right there. And notice that we're pretty close to 1,000,000 for each one of the 6 right there. Now, if you ran it, you might get different numbers. Obviously, every time you run this, you may get different numbers right there. So, but that's how we would. Is that out? What is that outside? Is that the speaker outside? That's there. Okay. So randomizing. Now, one of the things that we want to do is that we want to make sure that our random number generator starts off at a random place. That there. Otherwise, we get the exact same sequence each time, right there. So the way that we do this is that we seed our random number generation with this random seed right there. Now, the random number generator, if you don't seed it with a random, that there, it will give you the same results every time. That's useful for debugging. But if you want a truly random number generator, you have to seed it and tell it that there. And what we normally seed it with is the clock right there. Randomizing. So it's called SRAM, which the S actually is for seed. Well, they use the word seed right here to produce different that there. And the way we normally do that is we use, the SRAM, and we could give it the same seed every time. But normally what we would do that there is, you'll hear they're asking for the seed. We don't want to ask for the seed. What we normally do is we would normally use the clock, it's the time. And time is a function that reads the number of seconds that have passed since midnight on January 1st, 1970. I don't know why they picked January 1st, 1970. But it's the number of seconds that's passed. And every time you run that program, the number of seconds have changed. So therefore, you get a different seed every time. So we usually somewhere in the beginning of your program, you could do it in main, you could do it, I wouldn't reseed it every time, just do it once in the beginning of main, just do an SRAND time null and just pass it nothing right there. And that will just simply seed your random number. And there's nothing magical about it. You just need to include that if you're going to do random number generations. You just need to seed it right there. However, since we're using time, we have to include time.h right there. So right there, scaling again, this is our normal, this is the way we did it right there. So that there, this actually repeats different things. Our general form is n is equal to our starting value, our rand, modulus, how many values we have. So if you want a random number between 50 and 100, or 51 and 100, that's 50, 50 different numbers. But so it would be 50 plus rand. Actually, it'd be 51 plus rand percent 50. You want a number between 10 and 20, it would be 10 plus rand percent 10. So this is the general for the first number in the sequence, and then B is our scaling factor. So this is the how we would generate. And if I had a final exam, I would probably always ask that as a question. What would be, how would you generate a random number between 500 and 600? Right there. But since we don't have a test, you don't have to memorize that. Right there. All right, this gets into the game of craps, and I'm going to kind of wrap up with this discussion because this is this week's assignment. You're going to modify this game, so that there, and it's not an easy project, by the way. Don't think you're going to do it in 2 hours. It's going to take you a little bit of time. Both the ones I gave you are fairly complex. That there, so All right, the way that this does is we throw 2 dice. And you're going to get a value between 2 and 12. So if you get a 7 or 11 on the first throw, you win the game. If you get a 2, 3, or 12, you lose the game. You've lost. If you get something other than that, 4, 5, 6, 8, 9, 10, that becomes your point. So you keep throwing the dice until you reach your point. If you reach your point, you win. However, if you throw a 7 before you reach your point, you lose. Now, if you look at the number of possibilities of the dice, throwing the dice, 7 is the most likely number that you're going to get. It just turns out that 7 has the most possibility right there. So that you sometimes get, if you don't throw a 7 on the first time, then chances are you may end up throwing a 7 before you reach your point right there. So, but 7 or 11 on the first row. If you play this game and simulates the throwing of the game, I've gave the assignment before. Your assignment's different, where I've had somebody play 1 million games of craps, and looking at the percentage of wins versus losses, and what you would find if you played 1 million games of craps is that you would lose 52% of the time and win 48% of the time. It's close. And the reason, and it's close enough where the casino gets you playing because you feel like you're winning sometimes up there. But in reality, there's something in probability that applies to gambling. It's called the law of large numbers. Has anybody ever heard that before? The law of large numbers means that the more you perform a certain task or do a certain thing, and the results of that particular action results in, a win, loss, or a result. The closer you get to the actual probability. If I walk into a casino and I pull the one-arm band, the slot machine, and that one-arm band is programmed to pay out 40% of the time and take my money 60% of the time, I could walk in there with 5 one-ringgit coins. That there are 50-cent coins. There's not one-ringgit coins. That there, I'm thinking dollar coins in the U.S. But I could put in a 50-cent, pull the coin lever. If I did that once, I may win. If I did it 10 times, I may actually win seven times and lose 3 times. But if I pull that lever 1,000 times, I'm going to get closer to losing 400 or 600 times and winning only 400 times. If I pull that lever 1,000 times, 10,000 times, I'm going to get real close to losing 60% of the time. So casinos make their money on the fact that they keep those odds somewhat close to 50-50, but always in favor of the house. So that's the way this game works right there, is that the longer you play, the more you play, the more you're going to always lose right there. So there, and again, whoever wrote this book was not Muslim and didn't care about trashing gambling, but this game is a really good example of why you don't gamble, because you're almost always going to lose right there. So this is the code, and again, we do something different here that we haven't done before, and that is we declared an enumerated type. So that's an important part of this code that we haven't talked about before. Enumerated types are actually integers that we've defined here. Enumerated status means continue, won, or lost. So we threw a dice, And every time we throw the dice, we either win, or we lose, or we keep throwing. Right there. So if we're going for a point, so we keep throwing right there. We'll have a loop where we keep throwing until we either win or lose. We have another function called roll dice right there. And we'll look at that. In main, we initialize our random number generator. And int, we declare a variable for my point. Game status, right there, we declare a variable. Now, this is something interesting. This, we're defining a type. And a type is like int, bar, int, float, char, string. So status is actually a data type. So we can declare a data type called days. And our days could be Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. We could declare a data type called month, and we name them January, February, March, April, May, right there. So we can have, this is a type we've defined right there. So again, in our code, we could say status or game status is equal to continue, or game status is equal to win, or game status won, or game status lost. It makes our code more readable. We can write our code and not do that and declare a variable called game status and declare as int, and we treat continue as 0, 1 is 1, and loss is 2, right there. So that's there, because that's what the compiler is going to do anyway. But it just makes our code a little easier to debug and read if we use enumerated types right there. So here we go. We have a switch right there based on the sum of the dice. So the first thing we're going to do is we declared a variable called sum, and we roll the dice. And we'll look at roll dice, but it's going to return a number between 2 and 12. Right there. So the first thing we do on the first roll, if it's a 7 or 11, game status is equal to 1. Or 1, not the number 1, but I won the game, right? Break. If it's a 2, 3, or 12, game status is loss. We lost the game. We break. Then we have our default. If it's anything else, continue the roll. Player should keep rolling. And my sum is, remember the point, and my point is, and we break. Now this is to play one game right there. Now, here we go into the fact that while continue is equal to game status, if we've won or lost, we skip this loop altogether, this while loop. This right here, this loop here is where we keep rolling until we either get we win the game or we lose our game. Now you're going to have to enter this in for the assignment for next week, so that there, so or 2 weeks, whenever I set the due date. But that there, and actually this kind of looks weird. If 7 equals sum, I think this is an error. I think that's going to be sum equals 7, right there. I've never put the constant on the left side, but it could that there. But you keep that there. And this plays one game right there. This plays one game right there. Now, in the assignment, you play 1,000 games, or you keep playing until you get tired right there. You repeat, that there. So, but this is one game of craps. This is the shell of the assignment for next week right there. So this is our roll dice. Now, if you're going to play 1,000,000 games, you don't necessarily want to print out the result of each roll. That would get kind of tedious something there. But this is just for debugging, for seeing how it works. Die 1 is equal to, again, we throw 2 dice, so we have to add the 2 together. So, and this returns die 1 plus die 2, right there. So, that there. Player rolls. At the first time he rolled a 11, so he won. Here he rolled a 5, and he rolled 3 times before he got a 5, so he wins again. Right there. Here he rolled a 2, he lost. Here he rolled, his point was a 7 or a 10, but on the next roll he got a 7, so he lost. So this is how the game is played, right there. And I can almost guarantee you, if I gave you the assignment, is to play 100,000 times, and just tell the number of wins and losses, you'll find that it's slightly less than 50% that you win, right there. So this explains that code in more detail, right there. So, and this explains the enumerated type, right there, enumerations. And this goes through, and this just explains the game. And I kind of went through the code already. You can look at that there. I'm not going to read this. Right there. 2 functions. We only have 1 function we wrote in there. It's called roll dice, right there. We're using main, right there. I'm going to stop at this point. I'm not going to get into this. I'm going to skip storage classes and come back Monday and probably talk about. I don't want to get into storage classes. Scope rules, I'll mention a little bit about that. And then I think the last thing in this chapter is recursion. So we'll finish this chapter on Monday, right there. But you've got plenty to keep you busy out there. Over this weekend and probably a good part of next week, you'll be sitting behind a computer figuring out things right there. So, and remember that you will submit these electronically through VLE. So you'll submit your code along with several runs of the code. But there's 2 assignments, as I recall. Someone pointed out that I put an assignment up. I forgot that I put it up, but it's still a valid assignment that there. And then I gave the assignment there. Those are the 2 C programming assignments that we're going to be doing. There may be a C project when we finish C, but those are the 2 C programming projects that I'm going to be grading right there. So I may count this one as the project. So this one may count more than the other one. I haven't decided that there, because after scope rules, there's a lot of scope rules right there, but I'll fly through that. And then recursion, and I'll talk briefly about recursion. So we'll finish up this chapter on Monday, and Monday probably won't be a really terribly long. That there, I'm going to wrap this up. Actually, I thought today was going to be long, but it's only 45. I talked fast, didn't I, today? So, okay, well, that's fine. You've got plenty of work to do, so I don't really worry so much about that there. And to be honest, you learn more by writing these programs than you do by listening to me. Right there. You learn a lot more. So if you've got questions on it, you can send me a message through Facebook to answer them, or you can wait till Monday and I'll answer questions. These deadlines are not fixed in concrete, but don't abuse it too badly. That they're obviously, if it takes you a few days longer, I mean, I'm flexible on due dates within reason. But I know this is also, some people will abuse that and take till the end of the semester if I don't put a real deadline at some point. All right, I'll see you on Monday then.